Hello and welcome to Conf42 DevSecOps 2024. This talk is From Pain to Gain, Vulnerability Management Developers Won't Hate. And I'm your host, Anthony Laiuppa. A little bit about me. I come from a background in information technology and software development with over 10 years of experience. In the past, I've worked as a systems administrator, developer, DevOps engineer, security engineer throughout numerous industries ranging from finance, healthcare, industrial, electronics and hardware, business intelligence, from large companies all the way down to the smallest of startups. So I've truly experienced what it is to work in large organizations where change is metered and small organizations where they move agile, to put it one way. Every industry has its own unique set of compliance and regulations that really dictates a lot of how they secure their systems and, in turn, manage vulnerabilities. And this can stoke a little bit of ire between the remediators, the defenders, and other parts of the business as priorities are fought for. So let's run over some of the goals for this talk, shall we? First, we'll review conventional vulnerability management to make sure we're all starting from the same place of mutual understanding. We'll examine advancements in tooling and how they can augment our existing processes. Look for any opportunity to deploy some automation, discuss vulnerability analytics and reporting, and hopefully leave listeners with ideas on how they can help their organization more effectively manage vulnerabilities. So simply put, what is the gain here? The gain is, of course, aside from developer happiness, time. Time is money. All the time we spend triaging, remediating, fighting for remediating takes away from writing features, writing business logic, helping our bottom line. So let's see what we can do to reduce the sheer volume of vulnerabilities so that developers can focus on what they do best, developing the product. So before we get into that, let's go through a little bit of a refresher on vulnerability management. A couple of key terms that you may or may not be familiar with. A vulnerability is a software flaw, glitch, or weakness that could be exploited by an attacker. We will use this term interchangeably with the shorthand vuln. An exploit is a method or piece of code that takes advantage of the vulnerability or glitch in the software. Pretty straightforward. CVSS, Common Vulnerability Scoring System, a method used to supply qualitative measure of severity. So CVSS has had a couple of versions that have had different scoring rubrics. Ultimately, the goal is the same: to help you understand how severe the vulnerability is. However, CVSS is not a measure of risk. To be able to accurately measure risk would require an intimate knowledge of your organization and infrastructure that the rubric just can't have any knowledge of. Next, a term that you may or may not be familiar with already, EPSS, Exploit Prediction Scoring System, a data-driven effort for estimating the likelihood a vulnerability will be exploited in the wild. EPSS was actually developed with the goal in mind of helping assist network defenders to better prioritize remediation efforts. This will be a key point later on. Finally, CVE, Common Vulnerabilities and Exposure. That's what CVE stands for. It's mostly a list of identifiers for vulnerabilities. So when folks commonly say CVE, they're actually referring to a vulnerability more so than the overarching list comprising all the vulnerabilities, which is to say when somebody says, oh yes, look at this CVE, they're referring to an identifier or single vulnerability such as CVE 2021 44889, which for those who know, that's log4j, one of them at least. So where exactly are all these vulnerabilities? Vulnerabilities fit into every piece of software because at the end of the day, vulnerabilities are mostly just bugs. So packages, libraries, binaries, dependencies, images, Amazon machine images, Docker images, open container images, vendors, workstations, servers. If you can think of it and it runs software, it can have vulnerabilities. So let's dig a little bit deeper into the kinds of vulnerabilities and where they are. A great place to start is with the difference between a direct and a dependency vulnerability. A dependency is something your code will rely on to do its job. If you're using Python to make HTTP requests, then that would be the requests library. Your code is dependent on the requests library to perform HTTP operations. So a direct dependency vulnerability is when your library or code base explicitly imports a vulnerable package. A transitive vulnerability is when your dependency has a vulnerable dependency. So without getting too lost in the murky waters of that, let's look at some clear-cut examples to help make things evident. So first off, this direct dependency example. On the left, you'll see our package.json file. We import Lodash version 460. On the right, you can see the scan results for this package.json and Lodash 460. It has a critical, some highs, and some mediums. Next, our transitive dependency example. It's pretty easy to see how things can get lost because on the left in our package.json, we import handlebars version 400. And on the right, we can see that not only is handlebars marked as vulnerable, Minimist and Uglify.js are as well. However, we didn't directly import those packages, did we? Handlebars imports Optimist, which imports Minimist, and thus we have a transitive dependency vulnerability. So it forms a little bit of a hierarchy. Now let's take a look at how you could end up with a Docker image that has vulnerabilities in it. In this case, we've got a couple of different examples, starting with Chromium. So here we have the Chromium version pinned to 93, which, as it is quite old, time has gone by and vulnerabilities have been discovered in this version of Chromium. In this context, it is a binary. However, it can also be referred to as a package. You install it with your package manager, APK in this case, since this is an Alpine-based container image. Following that, we have Node.js with a little caveat that may help future remediators and maintainers. Installed packages in your Docker file should be pinned, much in the way that Chromium is. This makes it evident what version you are running and helps provide clarity into the image. Otherwise, you really don't have much of a way of knowing exactly what version of Node was installed without starting the Docker image and examining the file system or running Node version and looking at the output. Finally, one more time, we install a vulnerable dependency or library or even package to really help drive home the point. So why look at a Docker file that makes a vulnerable image and a code base differently? In this case, it could be that you're developing your code and you scan it and your scan results come back clean. However, you get a message from your security team later on that your service is running vulnerable. And this can be because of the other packages that are installed, not just directly through the code base, but in support of the code base, such as Chromium. So in this example, perhaps we have a suite that performs user interface tests for the front end using the Selenium WebDriver and Chromium. So maybe the version of Selenium on its own or the other NPM dependencies aren't vulnerable. However, if Chromium is, then you wouldn't really notice that without scanning both the code base and the Docker image. We'll circle back to that a little later on. While we're here, let's run through some more vulnerability management frequently asked questions. Where do vulnerabilities come from? Security researchers discover vulnerabilities every day and disclose them responsibly to maintainers, Then a CVE numbering authority will issue an identifier for them, or CVE, and hopefully after the patch is available. Not always the case though. Sometimes there's no fix available, or even worse, it'll be a won't fix. How do we find vulnerabilities? This really refers to the we in question. If you're a security researcher, it could be through code analysis, it could be through fuzzing or reverse engineering. However, in our context as defenders, remediators, we'll simply find the vulnerabilities by using a vulnerability scanner. What if we cannot patch our vulnerabilities? An exception may be granted in cases where there's an inability to patch within a defined window or service level agreement, which is just to say a set number of days or time period the organization will commit to remediating a vulnerability. As I said before, there's not always a fix immediately available, or in some cases, it'll be a won't fix. So in this case, broadly, an organization may work to grant an exception to the vulnerability, as it just plainly cannot be fixed within a timely manner. Finally, how often should we be scanning? As far as a best practice goes, we should always be scanning. Scan the dependencies on your local machine while you're developing. Scan in your CI pipeline, your continuous integration. Maybe scan the artifacts before they get deployed. And of course, scan them in production. Scanning early and proactively will help you identify vulnerabilities or out-of-date packages and help you better plan your development work so that you can work on upgrading those packages. Sometimes it's not always the easiest thing to do. Perhaps in our previous example, Selenium is dependent on a certain version of Chromium. Until we move our version of Selenium up, we can't really move our version of Chromium up. However, our code base is very heavily dependent on Selenium version 3, and version 4 is a major version upgrade. There will be breaking changes requiring us to refactor our code. So sometimes remediation could be as simple as just changing the number from version 4 to version 4.1. However, other times it could require extensive amounts of work. And as a result, this could create a little bit of a delay. So looking at traditional vulnerability management programs, prior to the advent of the cloud and more advanced tooling and all the work that's been put into this field, in the past, folks would set up scanning infrastructure. This would be something akin to a central server that will actually conduct the scan. Then they would put agents on all of the various machines. So perhaps you have your scanning server and you have your web server running a Apache server or Nginx reverse proxy to serve your web application. An agent will be placed on the host to scan the host or relay the information to the central scanning server to process. Finally, scans will be scheduled. So typically at an hour where there is less traffic so as to not potentially impede operations if the scan could be resource intensive towards the CPU. After all, if our users are trying to use our web application, the last thing we would want is to slow that down because we're busy checking the server for vulnerabilities again. So after the scans are complete, a large volume of results may come back. This is where the analysts will come in, or if unfortunately there are no analysts, where the code owners will be responsible for triage. So a large part of triage is working to omit noise. Noise in this context doesn't mean decibels, it means the sheer volume of results and parsing out false positives. So when you have a lot of false positives, you would say you have a lot of noise. So reducing the false positives and noise will help you focus on risk assessing and triaging actual vulnerabilities. So for example, if the scan results come back that your Apache server is vulnerable, however, it's only vulnerable if you have a non-standard configuration or load in a module to do some sort of audio processing that is not a default, then that is where you would take your triage and say, okay, we don't actually load that module to our Apache server, so we're not really vulnerable here. However, if it turns out that you are vulnerable, then the next step would be to contact system owners or the folks who will be doing the remediation to relay them the result, the true positive finding, and the inherent risk associated with the vulnerability. So if it's on a web server and it's truly critical, then that is a server that is exposed to the internet where malcontents could be also scanning and find this vulnerability as well. Once remediators have come up with a plan, slotted the work, and gotten it done, they would typically schedule a maintenance window, again, at a late hour so as to not potentially disrupt service. And in some cases, depending on your release process, it could even require a change control board or additional steps. In a best case scenario, you would be able to vet the updates in a test lab before deploying them out. So this is a little bit of traditional vulnerability management prior to the advent of cloud computing or many DevOps processes. Also, conventionally, the table on the right is really reflective of a lot of different standards. So picking a security framework and looking at its suggestions for what service level agreement or window would be best to target remediating a critical 15 days, a high 30 days, medium 60, and so on. Now, this is a little bit of a one-dimensional approach. It's critical, so it's 15 days. However, as we'll see with the increasing number of vulnerabilities coming out, this may not be the most sustainable or pragmatic approach. And of course, there's always the, hey, we've got a large list of scan results. Here you go, dev team. Here's an Excel sheet of everything we need you to remediate. We looked at it. These are vulnerable, of course. Here's some challenges faced by conventional programs. There's resource constraints, of course, staff shortages, or perhaps a lack of budget to secure further tooling or automation or additional resources. This very flat approach to severity and service level agreements. The ability to document known issues. So historically speaking, standards and documentation have been in flux. It is only recently that more standards such as SBOM, Software Bill of Materials, or Cyclone DX, or Vulnerability Exchange have come out to help everyone standardize on communicating the status of vulnerabilities. We'll examine that a little bit more later. There's the response. So if log is announced, or perhaps Apache struts, how quickly can you respond? With large, well-known incidents, we know that the answer is sometimes not fast enough. So being able to identify and track vulnerabilities will help you respond to them before bad actors are able to identify the vulnerabilities themselves and exploit them, which could in turn lead to a breach. The sheer number of vulnerabilities is increasing. Every day there's more software written, there's more eyes on the software, and more folks looking to exploit the software. On top of that, there's the issue of, with more vulnerabilities, there's more fatigue experienced by maintainers. As maintainers have to frequently stop feature development to assess the real risk behind vulnerabilities, this creates fatigue. Of course, more time spent on vulnerabilities is less time spent on features, which is not anybody's favorite thing. Hence the origin of the talk title and our goal of getting to a vulnerability management process developers don't hate. Finally, tooling. There's the burden of maintaining your scanning systems, keeping those agents up to date, keeping your scanning infrastructure available, and of course, perhaps a lack of features or integrations that will help make things easier, whether it's integrating with your favorite third-party tracker or advanced filtering, things like that. So let's look at what we can do to revamp vulnerability management. By combining a little bit of our favorite cloud features and DevOps methodologies, we can do some truly wonderful things. For example, event-driven architecture has become more prominent. Cloud providers such as AWS, Amazon Web Services, provide event buses. They provide their own scanners. So AWS Inspector has the ability to act either with an agent, of course, as we mentioned, or agentless. So they're actually capable of scanning resources in your cloud without you having to explicitly set up an agent and configure it to relay those results. This is a huge advent, as we don't have to worry about those maintenance overheads we described before. On top of that, the cloud providers now offer numerous approaches to automated patching, whether that's using Systems Manager to create a patch plan and have it patch your infrastructure for you automatically, or the various deployment mechanisms, which can actually also be leveraged here to update your systems without incurring any downtime. Things like rolling updates or blue-green deployments, or being able to patch your servers without requiring a reboot. In the past, downloading a security update frequently required a reboot, which of course requires downtime. Not only this, but there are also multiple vendors entering the space as well. Everyone is proposing their own scanning feature set as well. So there's a greater variety of options to help you find a scanning solution that will easily plug into your architecture. On top of this, the folks who are setting the standards for vulnerability, the folks running CVSS or setting EPSS, are helping change the equation. They're helping put a focus on prioritizing what is truly critical so that we can focus on remediating that first. There's also an increasingly larger number of analytic solutions available for better reporting and tracking. So not only are we just receiving large volumes of data about our vulnerabilities, but now we're actually able to quantize them and display them visually to help get greater insight into what it is we are up against. And even better, everybody's working on their integrations. So now perhaps your scanning tool can help you click and just create a Jira ticket and assign it to your favorite development team to get it on their board for their sprint. Of course, with the advent of newer technologies and newer systems, maybe we just move from sending emails to sending Slack messages, but that's maybe not the best way to go about this. So let's talk about one of the newer things that has recently come into standard, the Vulnerability Exploitability Exchange, which is a document that acts as a form of security advisory. So when I'd mentioned previously that documentation was a struggle, part of the struggle was coming to a standard on how we're going to communicate what is or isn't vulnerable. This helps us with prioritization. Specifically, one of the greatest gains of the VEX documents is that they allow turning off security alerts from scanners for vulnerabilities that are known not to affect the product. Of course, the VEX standard and documentation is in an early stage of adoption. So not all scanners may necessarily support the usage of VEX documents. Next up, we have code reachability. So code reachability is, in a nutshell, the process that determines if a vulnerability in code, libraries, or containers can be exploited in a given environment. So looking at a couple of categories of code reachability, we have reachable, where the vulnerable function is called in a manner that it can be interacted with. Conditionally reachable, the vulnerability function is called in a manner that can be interfaced with if certain criteria are met. Perhaps your Boolean statement evaluates to true, and now we can access the vulnerable statement or not. Always reachable. Just importing the vulnerable package makes you susceptible to being exploited. The vulnerability is more or less omnipresent in that situation. Finally, unreachable. The vulnerable code is not present or not able to be interacted with outside of the program's runtime. Even better, some vendors are able to automate this process for us. This can dramatically help relieve the burden of triage by automating part of it. So let's go through some code reachability examples. So going back to our previous Lodash example, we have this code reachability demo package.json where we import Lodash 4.6.0. We can see it has a critical vulnerability along with some mediums and highs. So let's look at some code that actually uses this Lodash library. Can you spot which one is vulnerable? Let's take vulnerability CVE 2018-48.7. A prototype pollution vulnerability was found in Lodash versions less than 4.17.11, where the functions merge, merge with, and defaults deep can be tricked into adding or modifying properties of object prototype. So if we're looking at our two code snippets here, we can see we have one code snippet, merge configs, which returns a merged result of default config and user config based on our function, right? Takes in user config and we perform lodash.merge and return the result. In the second example, we have lodash again. However, we're calling the lodash.get function, hoping to retrieve the color setting of the user's configuration and return back what color the user has selected for their theme. In this case, the second code snippet is not vulnerable. It does not call merge, merge with, or defaults deep. However, the first one does. In this regard, the second code snippet would be marked as unreachable, and the first code snippet would be marked as reachable. This kind of distinction can help us automatically remove some of the effort of triage and reprioritize the order in which we address these vulnerabilities, resulting in more time spent where it matters. Putting this all together, let's look at an example of what a Vex document can do. So here we have the Get User Theme Setting project and a CI pipeline where we run our test. So first things first, we're checking our unit tests, right? Our unit tests are in fact passing. However, our pipeline is failing. We have it set to fail on criticals because we don't want to release critical vulnerabilities to production. And we're looking at the critical vulnerability in Lodash that calls the default deep. So checking our code again, same snippet we just looked at, we can in fact still see that we call lodash.get. And lodash.get, as we know, is not the vulnerability that is not vulnerable. So here we have VexCuddle. VexCuddle is a tool to help make Vex documents work. In a nutshell, by using this tool, we can have it automatically generate a Vex document for us based on the information here, which is where we will give it a not affected status and a justification of vulnerable code not present. So here we are running the VexCuddle tool, which now adds a vex.json file to our project. Now we will commit this to our version control system and then let the pipeline rerun. Great. So we've got it added to our version control, and we'll update our CI pipeline to now have our scanner respect our Vex document. So now that we have this all put together, let's head back to our CI system. Let's run the CI pipeline and see if we get a different result now. We haven't updated the dependency, so it still has the vulnerable code. However, we have triaged it, and we have been able to conclusively say that this software product is not affected, and we have clearly documented that using the Vex document standard. A large point of improvement would be if we could leverage a vendor's tool to perform the code reachability analysis for us and generate this Vex document. That would save even more time. Here we are. We can go ahead and see our tests still passed, but most notably, when we go back down to our scan job, it clears. Our pipeline is now green, and the vulnerability, as reported by the scanner, was ignored or suppressed. So going back, giving it some time to run, happy deployment. So this is one great example of how we can use Vex documents and tooling to reduce the burden of vulnerabilities in our projects. So let's rethink our production vulnerability management, because that's where the vulnerabilities matter the most, our production environments. It's where things are the most sensitive and also where they are most scrutinized by attackers. As before, our scanner is going to report our findings. What would be great is if we could have our exceptions applied to them. So perhaps your organization has made an exception because it can't patch something in a timely manner, or there's no fix available, or the risk was accepted. Next, we would like to inject our Vex documents or perhaps some code reachability analysis to remove or suppress additional vulnerabilities. Finally, we could also add some environmental factors in. Now that everything supports labeling and tagging across our resources, which we will very much demonstrate shortly, we can use this information to help guide our scanner along in further reducing the amount of vulnerabilities or increasing the amount of time for the service level agreement or remediation window to take care of this. Finally, why have to deal with creating a email or Slack message with a large Excel sheet of vulnerabilities when instead we can just work on integrating this into our work tracker of choice or GitHub, GitLab issues, whatever your version control is, to just co-locate the work to be done in a manner that fits into developers' work. In this case, we're thinking of redefining service level agreements. We're not using that flat chart anymore. We're automating the intake and triage of vulnerabilities. However, it does have a limit, which is the amount of information that's readily available. We do have more information than ever, though. Factoring in things like the exploit predictability or the code reachability or the network exposure, these aspects can make a noticeable difference. Even slight additions of information can help adjust the SLA for remediation. So if that critical is not truly critical, or it's perhaps only on an internal service that's not exposed to the greater internet, or if it's even just a running job that has no network reachability, we can take a little bit longer to remediate that vulnerability. For example, a high vulnerability that is part of a job and is only conditionally reachable may have its service level agreement extended due to the significantly lower likelihood of exploitation. Let's talk about some automation strategies on the other side of it, right? We've talked about using VEX documents and code reachability for the security workflows. How does this play in for the systems maintainers? We can use our favorite DevOps methodologies such as infrastructure as code or automation to create lower environments. In the past, creating a test lab was largely determined by your access to spare hardware or spare compute to run your VMs on your hypervisor or environment of choice. But now, with the advent of clouds and multi-tenant environments, we could perhaps spin up a lower environment or test in a lower environment prior to promoting it to a higher environment, such as production, giving us confidence that our patching will not break critical systems. Of course, we have continuous integration, CI pipelines, and these can run automated tests in tools like RenovateBot or even scanners to help us be proactive and informed, or in the case of RenovateBot, just remediate the vulnerabilities for us. DevOps automation strategies such as rolling deployments, blue-green deployments, instance refreshes, things like that, all of those deployment strategies and maintenance strategies play right into remediating with ease. So if you've thoroughly automated your deployment process, you've also automated your remediation process as well. There's some other great things you can do to reduce your attack surface. So things like packaging less in your deployments, using Scratch containers, making sure that dev dependencies or unnecessary packages aren't in your final product will also help slim out and reduce the amount of surface area that can throw vulnerabilities in scanners. So here's an example of deploying RenovateBot. So we're going to reuse our same code base and version control and CI pipeline setup that we set up before. So here's our Renovate config project. We followed the RenovateBot documentation. We've added this Renovate JSON file to our project to onboard it. Now we can go over to our pipeline for RenovateBot. This could be scheduled or ran by any CI job runner or infrastructure of your choice, right? So in this case, we can see that it ran and that it detected our project. And if we go back to our project, we can actually see that RenovateBot has opened a pull request. So this is great, right? It's done the work of detecting that there is an update available for a vulnerability. However, that by itself isn't enough. That's just a little bit of work. We still have to triage. Did it break anything? So if we just go back to our CI pipeline, we can see that just by having tests running, we know that this won't break anything, and we can clear it even faster to go to production to get this remediated. So here we see the next round of npm install. It says 0 vulnerabilities, and the scanner, of course, returns no further vulnerabilities. RenovateBot has updated the dependency. Our tests have validated that our core business logic is not broken, and now we can proceed onward with the upgrade without having to do extensive amounts of checking to make sure we haven't broken anything. Now, getting a little more creative with the event-driven flow and what the cloud can offer us, Let's take a look at integrating our cloud vulnerability scanner, which in this case we'll use Amazon for our demo, to fire off events that will then be picked up by a serverless function and tracked in our work tracker of choice, which in this case we'll use Jira. So here we are, we have a Jira board that will receive our ticket. Here is an example of a Lambda function that is wired up to an SQS queue. And here's a little bit of infrastructure as code that we use to manage our deployment, same way a DevOps team would use to manage their production services. We've set our event filter capture to find inspector events at a critical or high, and just a little bit of showing off our CloudWatch event targets to make sure that these events properly get routed to our SQS queue, which will feed our Lambda consumer. And then on the right, we have a package called Intentionally Vulnerable, where we've loaded a vulnerability to make sure that we can actually trigger a detection and see this workflow in action. We've also added some labeling to it, an owner that we can assign the ticket to in an automated manner, as well as some information about its exposure. So in this case, we've marked it as internal. So we'll go ahead and run our automated deployment using our infrastructure as code to spin up another serverless function in our cloud environment, in this case, the intentionally vulnerable Lambda function. So now that it's been created and applied, we can go over to our tracker and we can wait just a few brief moments for this to show up on our workboard. The idea being that the system is able to, in near real time, pick up on events from our security scanner and then assign them to remediators. Now, using information, as we've talked about before, such as labeling and tagging, we can also add more information to the ticket. So in this case, since we marked it as internal, it added 10 more days to the due date. And of course, it provides us an easy link for us to go view the package and its vulnerabilities in the console. Now, where this can get a little bit more enhanced is we could work on integrating with the code reachability analysis or VEX documents or exceptions. And we could also work on integrating with a database such as DynamoDB or your SQL database of choice to store this information. We'll touch on what we would do with that information later. So here we are waiting for things to reconcile in the user interface, which can be the slowest part. Ideally, we would want to see the vulnerability ticket move over to done. So in this case, what we've done to remediate is we've removed a vulnerable resource. We could, of course, release a new version of the package with an updated dependency. However, for purposes of this demo, it was just quicker to remove the resource. In some cases, the resources aren't needed. After all, there's no more permanent solution than a temporary one. However, I was remiss waiting for the vulnerability to move over to the done column. But as you could see, the issue itself still showed done. So the system was able to pick up on the closing event of the vulnerability and mark our ticket as closed. So this saves everybody a little bit of time as they're not having to waffle back and forth, updating and tending to the tickets as well. And of course, this opens us up for the opportunity to inject more information into this process to help either extend the SLA or remove vulnerabilities, whether with our VEX documents or through code reachability analysis. Let's take a word about Kubernetes. Right. So far, we've talked a lot about Docker container images and serverless functions and touched on operating systems. Kubernetes being fairly cloud agnostic, this approach could work in any cloud environment, which fundamentally is that all you need to know is what container images are running on your Kubernetes cluster, and you can queue up scans for them. In this example down here in the right column, we have an admission controller, which will receive all of the requests that are made to Kubernetes API to start pods, containers, daemon sets, stateful sets, deployments, jobs. And with this admission controller, we can actually start to take actions. So the first thing we could do is nothing. we could simply allow the manifested Kubernetes resources to begin running on the cluster. And we could send the information to our SQSQ and our Lambda system for processing, triaging, evaluation, and ticketing. Alternately, in the event that we didn't want to use an emissions controller or object on the Kubernetes cluster, we could just simply spin up our own resource, whether a serverless function or service, to periodically query the Kubernetes API for the list of container images and follow through with it. Now, one thing that is very innovative and helpful in this regard is that some vendors are releasing more fully fledged emissions controllers, which can actually even act as gatekeepers. So those emissions controllers could also perform tasks like assessing if a scan has taken place on the container image that's coming onto the Kubernetes cluster. If it's missing a scan, it could deny the resource from running on the cluster. This could be great if the cluster's been compromised and a threat actor is attempting to spin up their own resources on the cluster. This could be great for preventing critical vulnerabilities from being launched into production on your cluster. So this kind of shows both a more direct way of being on the cluster and intercepting things in real time, being event-driven, the event being that more resources or container images are asked to queue up and start on the cluster, or alternately by monitoring the cluster through an adjacent service that can authenticate to it. So circling back to what we said about our database prior, being able to quantify the amount of reduced risk and reduced exposure that comes from remediating these vulnerabilities will speak volumes about your program's effectiveness. Being able to show how quickly vulnerabilities were remediated when they mattered, and how many vulnerabilities were able to be downgraded so that developers could better spend their time. Aside from being more secure, you can directly translate time saved to development labor hours saved. Time is money. Most vendors and tools have some semblance of reporting. Depending on how you structure your program, you may have additional options as well. Since in our previous example, we were handling the intake of all the data, we could structure it however we'd like in our database to facilitate things like creating a vulnerability burn down chart over time, figuring out our average time to remediation for critical vulnerabilities, breakdowns by the team based on what labels are assigned to the Kubernetes pods or who the owners are, vulnerabilities by resource type, seeing what our most vulnerable resources are. There's a lot of possibilities here. You could even do things like leverage cloud native tooling. So you can take your Dynamo table and dump it to files in an S3 bucket, and then leverage Athena and QuickSight to query and index the database and generate visuals. Or you could take it more directly into your own hands and simply connect to your database and use a tool or library such as Pandas and create the visualizations yourself based on how you transform the data or process it. Every critical vulnerability may not be truly critical. It's important we know which and as fast as possible. Which is to say, just because you import log4j doesn't mean that you're necessarily exposed to being exploited by a log4j exploit. The sooner that we could turn around and identify with high fidelity these kinds of scenarios, the better and more secure we can be. So overall, our goal for revamping vulnerability management in a DevSecOps era is to help our development teams reduce the amount of labor they need to put into identifying, triaging, and remediating vulnerabilities. And by enhancing this, we can have better detection and response. The better we are able to track, identify vulnerabilities, the more we will know what we are susceptible to and when we are susceptible to it. Thank you, and I hope you've enjoyed the talk and you can at least come away with a couple of different ideas about how you can revamp vulnerability management at your own organization.